please subscribe to support the channel. You've been told your whole life that nothing can outrun light. But why does that rule seem absolutely unbreakable, even when we push matter to ridiculous energies? Light in a vacuum does about 186,000 miles every second, roughly 7.5 laps around Earth. And in modern physics, that number is the built-in speed limit for anything with mass. In Einstein's special relativity, space and time are tied together so that this speed sits at the top. You can push closer and closer to it, but if you have mass, the equations say you never actually reach it. At low speeds, things feel simple. You push, you speed up. More push, more speed. Near light speed, that story changes. In special relativity, as an object moves faster, its energy rises faster and faster. The curve bends upward, and close to light speed, it goes nearly vertical. Extra shove mostly gives you more energy, not much more speed. The universe basically turns your engine into a very expensive heater. Said in plain language, you can keep dumping energy into a particle and the speed climbs, but each new step costs more than the last. When you plug the exact relation between speed and energy into the math and try to hit light speed itself, the answer you get is brutal. You would need infinite energy. Infinite fuel never shows up, so anything with mass is locked below that limit by the structure of space-time, not by our engineering skills or technology level. That raises the next question. If you somehow had a way to go faster than light, what would really break? Would it just be a speed record, or would you tear up cause and effect? In relativity, faster than light motion lets different observers disagree on which event came first in a way that is not just perspective. It changes what counts as cause and what counts as effect. As long as no information outruns light, those different stories line up into one consistent history. Once something does, they do not. Turn that into a signal and the problem hits hard. If you and a friend could send messages faster than light, you can set things up so that, in some frames, the reply shows up before the original message is sent. With the right arrangement, you can receive a warning not to do something, and because of that warning, you never do the thing that was supposed to trigger it. You get a clean, logical loop. No single timeline fits, and basic causality falls apart. Physics cannot function with that kind of contradiction. So we test the limit directly. In circular accelerators like the Large Hadron Collider, protons run around a ring over 15 miles across, held by giant magnets and pushed by radio frequency cavities every lap. Engineers pour in massive electrical power just to make those already fast particles a little bit faster. When you measure their speed, they are moving at more than 99.9% of light speed. So close they might as well be light beams. No matter how much extra energy goes in, those protons never cross that last tiny gap. They just hit harder when they collide. Nature does the same experiment with cosmic rays, particles launched by supernova explosions and black hole environments, hitting our atmosphere with energies beyond anything we can build right now. When physicists reconstruct their motion, those particles are again just under light speed, never over. Everything we see, from human machines to extreme cosmic events, says the limit is real. And just when that sounds settled, quantum physics throws something stranger at you, a kind of connection that doesn't try to outrun light through space at all. It acts as if distance barely matters. This is quantum entanglement. In labs, scientists create pairs of particles, often photons, whose properties are linked by the way they are produced. One goes left, one goes right, and detectors sit far apart, sometimes different buildings, sometimes different towns. When you measure your photon, you get a random result. When someone else measures the partner photon far away, they also get a random result. But when you later compare data, the two sets of outcomes are correlated in a way that can't be explained by the particles carrying simple pre-written instructions. The pair behaves like a single shared state stretched across space, not two separate objects that decided what to show you in advance. These are not just fragile tricks on a table. Experiments send entangled photons through city-scale fiber networks, across mountain valleys, even between ground stations and satellites hundreds of miles up. Locally, every detector sees only noise, just clicks that look like 50-50 coin flips. When teams bring the logs together, line up the timestamps, and crunch the statistics over many events, the quantum pattern appears across huge distances. You can even try to clock this weird connection. Set the detectors far enough apart that no light signal could get from one to the other in time during each measurement. And then ask, if I pretend there is some influence jumping between the particles, how fast would it have to move to match the timing we see? When researchers run that analysis, they don't get slightly above light speed, they get lower bounds that are absurd, thousands, sometimes millions times faster than light, at least. So that sounds like you have finally found something that outruns light, but there's a catch hiding inside the data. You can't control these outcomes to send a usable message. Each side sees only random clicks. Nothing in their local stream tells them what the other side chose to do. The instant connection shows up only when you compare results later, with light-speed communication. So you're left with a universe that seems to be saying two things at once. Nothing that carries information can outrun light without destroying causality, and yet entangled particles behave as if they are tied together by a link that doesn't care about distance and blows past any normal speed limit. That tension is the tightrope you're going to walk in the rest of this story. So the question on the table now is sharp and simple. Are you looking at something that really goes faster than light, or at a completely different kind of connection that only looks superluminal from the outside, while keeping causality safe behind the scenes? To answer that, you need to see what entanglement actually is, and just as important, what it is not. How can two particles be in different places and still count as one system? That's what entanglement forces on you. In a lab, a laser hits a crystal a few inches long and produces pairs of photons, tiny light packets flying in opposite directions at light speed. Your first instinct is to say, this photon is already vertical, that one is already horizontal, or this one is spin up, that one is spin down. Quantum mechanics says no. Before you measure, the pair has one shared quantum state. It lists all possible linked outcomes with exact probabilities, but doesn't give either photon its own fixed values. In plain language, the theory will only tell you statements like, if you later measure both with a certain setup, there's this chance you see one result here and a related result there. Until a measurement happens, the math treats the pair as a single object spread over two locations, a superposition of joint possibilities. How can a basic two-choice question, up or down, horizontal or vertical, turn into a test of whether reality is local or not? For many quantum systems, including spin for electrons and polarization for photons, measurements give only two outcomes. You set a detector angle, it interacts with the particle, and you record two answers. For a single, non-entangled particle, those answers are random, with odds set by how you prepared it and how you oriented the detector. With entangled pairs, you and a partner sit far apart, each with a detector. Every time your detector clicks, you log the time, the setting, and the outcome. Your partner does the same. Alone, your data look like random coin flips. Your partner's data look the same. The shock comes when you line up matching events. For some relative angles, whenever you see one outcome, your partner almost always sees the opposite. For other angles, the agreement rate changes in a very specific way. Over many trials, the pattern matches quantum predictions. The crucial point is this. When you repeat this at many angles and analyze thousands or millions of pairs, the statistics do not fit any picture where each photon left a source with a fixed list of answers for every setting. It is not enough to say they agreed everything in advance. The numbers rule that out. You end up with unpredictable single results, but joint results that obey a rule no simple local hidden script can reproduce. That is exactly why Einstein pushed back. How can a theory that keeps matching experiments still be called spooky by the person who built relativity? In 1935, Einstein, Podolsky, and Rosen looked at this kind of entangled setup. They argued, if measuring one particle lets you predict with certainty what you will get from the other, Even when it is far away, then either some influence travels between them faster than light, or the particles carried extra hidden information that quantum mechanics does not describe. Because relativity says no physical influence should outrun light, Einstein rejected the first option. So he favored the second, the hidden variables idea. In that view, the quantum state is a summary, not the full story. There's a deeper layer with ordinary local properties that would remove the spooky action at a distance. Einstein expected that later physics would find that layer and restore a picture where everything important travels at or below light speed. For a while, that was a serious hope. At the same time, a very different misunderstanding took off outside physics, the claim that entanglement is about mind, intention, or cosmic connection. How can something that sounds like instant connection not be telepathy or a consciousness effect? Because none of that appears in actual experiments. In quantum mechanics, an observer is any physical system that records a result, not a person. A detector, a sensor, a memory chip, all count. No one has to watch a screen at the moment a photon hits. You can lock the whole setup in a room, automate everything, and let it run for hours. Later, you copy out the stored data and run the analysis. The same entanglement pattern shows up. The universe did not wait for human awareness. There's no term in the equations for belief or mood. Entanglement does not let you read thoughts, link souls, or make the universe react to your attention. It's simply a precise pattern of correlations between measurement results when particles are created in a shared quantum state. Once you strip away the mysticism, the next question is practical. Is this just a fragile tabletop trick, or can you generate entanglement on demand and push it through real-world channels? How does this look when you scale it up? In modern labs, nonlinear crystals a few inches long, pumped by lasers, generate huge numbers of entangled photon pairs every second. Optics steer those photons into glass fibers, the same kind used for internet backbones, or send them through open air between buildings and mountaintops. Some setups send one photon to a ground station and the other to a satellite hundreds of miles above Earth. At the receivers, single photon detectors sit behind devices that set the measurement basis, such as polarizers at chosen angles. Electronics tag every detection with a timestamp and log which setting and which outcome occurred. Over minutes or hours, this builds large datasets of paired events. Then, both sides combine their logs and count correlations. Again and again, across fibers, free space links, and satellite links, the observed correlations match quantum formulas and violate the limits that any local hidden variable model must obey. Different groups with different hardware on different continents see the same basic behavior. Two particles acting like one state stretched over distance, in a way classical local stories cannot copy. So now you have a clear picture. Two particles, one shared state, random local results, strong non-local correlations, no telepathy, no magic, just lasers, crystals, fibers, detectors, and statistics. Einstein's hope for a local hidden description is no longer just philosophy. It's something you can attack with math and experiments. The next step is to turn maybe there are local hidden variables into a strict numerical limit, and then ask whether nature respects that limit or breaks it. That is where Bell's theorem hits, and it's where local realism runs into serious trouble. So if entanglement is real, and the correlations really are that strong, how do you rescue a normal, local world where nothing talks faster than light? The classical escape plan sounds very reasonable. You say, all right, maybe each particle just carries a secret instruction set from the source. Each photon leaves a crystal with a hidden script that says for every possible angle you might use, here is the result you should show. Up or down, horizontal or vertical. When you and your friend run the experiment, you're not watching anything spooky happen at a distance, you're just revealing pre-written answers. That story feels safe because everything important gets decided locally at the source before the particles separate. No influence has to travel between them later. Einstein and others leaned hard on this kind of idea. In their view, quantum mechanics is like a blurry snapshot, a useful approximation that doesn't show all the details. Underneath, there are hidden variables, extra properties that decide outcomes in a clean, predictable way. Once we discover them, quantum randomness and non-locality go away, replaced by ordinary cause and effect moving at or below light speed. So where is the catch? Why doesn't that comfortable picture survive contact with the math? In 1964, John Bell sat down and did something ruthless. He took the vague sentence, "maybe there are local hidden variables," and turned it into specific numerical limits you can actually test. He assumed exactly what Einstein wanted, that each particle carries local instructions that tell it what outcome to give for any measurement angle, and that nothing you do to one particle can instantly affect the other, especially once they are far apart. From those assumptions, he derived inequalities, basically upper bounds on how strong the correlations between your results and your friend's results can be, when you both choose between different detector settings. You can think of them like a scoreboard limit. If the world runs on local hidden scripts, the combined statistics of millions of measurements can never push your correlation score past a certain threshold. Cross that line, and the whole local hidden variable program is dead. Quantum mechanics, on the other hand, does not respect that limit. When you calculate the expected correlations for entangled states at different detector angles, the predicted pattern goes beyond Bell's classical ceiling. That means you now have a clear yes or no test. Do the experiments line up with a local script model, or do they line up with the quantum model that has no such constraint? There is no middle ground left. That is why Bell's work is such a big deal. At that point, everything hangs on what happens in the lab. In the early 1980s, Alain Aspect and his team in France set up one of the first convincing tests. They created entangled photon pairs and sent them to two detectors about 40 feet apart. The key twist was that they did not fix the detector settings in advance. While the photons were already moving, they rapidly switched the measurement angles using fast electronics, so the particles could not know ahead of time which setting they would face when they left the source. Over tens of thousands of detection events, they recorded every click, every setting, and then ran the statistics. The result? The correlations between the two sides did not obey Bell's inequality. They broke the classical limit in exactly the way quantum theory predicted. Local hidden variables did not just look awkward, they looked wrong. You could still argue about technical loopholes. Maybe the detectors were not efficient enough, maybe communication could sneak through, but the basic pattern was clear. Quantum predictions were winning. You might ask, did we really close all the doors that a determined classical model could try to slip through, or are we just seeing a clever experimental illusion? That question drove decades of work. Modern Bell tests push the two detectors much farther apart, sometimes more than a mile. They use ultra-fast random number generators based on quantum processes to pick the measurement angles on the fly, so there's no chance for hidden coordination based on pre-programmed patterns. The detectors themselves have become extremely good. Some are superconducting devices cooled to just a few degrees above absolute zero, able to catch a high fraction of the incoming photons. Experiments carefully align the timing so that in the space-time picture, each measurement is completed in a way that no light-speed signal from the other side could arrive in time to influence it in any reasonable reference frame. Then they collect huge data sets, hundreds of thousands or millions of entangled events. When they analyze those datasets, the violations of Bell inequalities show up with very high statistical significance, far beyond what you would expect from random fluctuations. We're talking many standard deviations, the kind of result where if it were wrong, you would have to believe in a conspiracy of errors across different labs, technologies, and continents. On top of that, different groups close different possible loopholes, and the story stays the same. Quantum mechanics keeps winning. Local hidden variable models keep failing. So what does that actually force you to give up? What part of your intuition has to be sacrificed? Bell's theorem, backed by all these experiments, corners you. You cannot keep both locality, in the sense that influences cannot act outside the light cone, and a strong form of realism, where outcomes are fixed by pre-existing properties that each particle carries with it, independent of how you choose to measure. If you insist on a picture where everything is determined ahead of time, you have to allow some kind of non-local link that coordinates results across distance, in a way that is not limited by light speed. If you insist on keeping strict locality, you have to accept that outcomes are not just revealing pre-existing values, that the act of measurement and the choice of settings are deeply tied into what reality becomes. There is no escape that keeps both classical comfort zones intact. Here's the key point though, and it connects directly back to the question of spooky speed. These non-local correlations don't die off with distance. Make the separation bigger, the pattern stays. Rotate the whole setup, run it at different times of day, put it in different labs, you get the same kind of violation of Bell's limits. Yet in every case, you still can't use those correlations to send the controllable signal faster than light. The connection that seems to outrun light is real in the statistics, but it carries no message you can encode or decode on its own. So you end up in a strange but very well-tested place. The universe doesn't work like a local hidden script machine, and the data refuse to be explained by anything as simple as pre-written instructions traveling at or below light speed. Whatever is tying these entangled outcomes together is deeper than that, but at the same time, it somehow respects the ban on faster-than-light communication. The next step is to push this as far as possible and ask, if you treat this mysterious link like an influence, how fast would it have to be, and what do those speed estimates really mean? How do you even talk about the speed of something that never shows up as a normal signal? One way is to push the geometry of space-time itself and see how hard you can make these correlations work. In some experiments, teams sent entangled photons through optical fibers to two labs separated by several miles. Each lab has its own detector and its own high-precision clock, often based on atomic transitions synced to just a few billionths of a second. The whole point is to arrange things so that from the point of view of relativity, the two measurements are space-like separated. There's literally no way for a light-speed signal to leave one detector and arrive at the other in time to influence that same round of measurements. That word space-like means something very specific. If you draw the space-time diagram, the event detector A clicks and the event detector B clicks are outside each other's light cones. There's no path moving at or below light speed that could connect them in the right order. The timing and distance are chosen so carefully that no matter how you tilt your reference frame, no ordinary influence can race across in time. Now you run the entanglement experiment under those conditions, and you ask, do the correlations survive or do they fade once you cut off any possible sub-light connection? They survive, and that's where things get uncomfortable, because then you can say, all right, suppose I pretend there is some influence that really does jump from one side to the other. How fast would it have to move to do its job? Researchers look at their timing data, down to billions or even trillions of a second, combine that with the physical separation, and use that to calculate a lower bound on any hypothetical spooky speed. It's like saying, if something is coordinating these outcomes, it had this much distance and this little time, so it has to be at least this fast. The numbers that come out are not gentle. They aren't a little above light speed. They are brutal. In some fiber experiments, the bound lands at thousands of times light speed. In other more extreme setups, depending on how you choose the frame and the geometry, the lower bound pushes up to millions of times c. That doesn't mean we actually detect a signal moving that fast. It means if you insist on a signal picture at all, relativity forces you to admit it's so fast that light looks slow by comparison. Look at what those setups actually do in detail. You have a source in the middle, or in one lab, creating entangled photon pairs and sending them down fiber optic cables that may run under roads, through tunnels, and across buildings for several miles. The photons take microseconds to reach the detectors at each end, which is a long time on the scale of electronics. At each detector, fast devices choose the measurement basis, often at the last possible microsecond, then record the arrival time and outcome. Over many hours, the system logs millions of events, each with a timestamp and a record of which angle was used. Later, you merge the two datasets and sort them, matching pairs that fit within tight timing windows. When you crunch those numbers, you see the same bell-violating pattern that small tabletop experiments give, but now stretched across miles and microseconds. If you try to blame a sub-light speed influence that starts when one detector clicks and then runs through the fiber or the air to the other side, the timing just does not work. There is simply not enough time for any light speed or slower signal to get there and still line up with the observed coincidences. Then take it off the ground entirely. In satellite experiments, one photon from each entangled pair goes to a receiver on Earth. The other goes to a detector on board a satellite hundreds of miles up, moving along its orbit. The light travel time between ground and satellite is on the order of milliseconds, which is a huge gap compared to detector response times. The satellite might link two distant ground stations, sending one photon to each, so they end up separated by hundreds or even thousands of miles. Again, each site has its own random choice of measurement setting and its own clock. They log detection times, settings, and outcomes. When the data comes back and you line up matching events, the same quantum correlation pattern appears, strong enough to break Bell's inequalities with no sign of degrading just because you added hundreds of miles of separation and shot one of the photons through the upper atmosphere and vacuum. Change a setting on the ground, record what happens, and the statistics in space still lock into the same structure, as if the distance barely matters. If you push the influence speed idea here, the lower bounds become ridiculous. Across satellite distances and millisecond timing, a hypothetical coordination signal would need to move tens of thousands of times faster than light, sometimes more, depending on the exact geometry and the frame you pick. The farther out you go, the more space-time you give your test, the more extreme the required speed becomes. From that perspective, the correlations act like they are either instantaneous or so close to it that the difference is impossible to resolve with current technology. This is where you have to be very careful, because it is easy to hear all of that and jump to the conclusion, great, we have a faster-than-light phone line now. That is exactly what nature does not give you. There is a hard catch. Correlation is not communication. At each detector, the results are still random. Every time your photon arrives, your detector clicks one way or the other with probabilities set by the quantum state and your measurement angle. But you cannot choose the outcome. You cannot force it to be a 1 or a 0 in a controlled way. Your partner on the other side sees the same thing, just a long list of random outcomes. If they look only at their local data, there is no trace of what you did, no pattern that tells them your choices or your results. The spooky structure lives only in the joint statistics, the way your outcomes and theirs are correlated when you compare notes later. That comparison always requires a normal light speed or slower channel, whether it's fiber, radio, or even hard drives carried by hand. So even when the timing analysis screams that any hypothetical influence would have to be insanely fast, you still don't get a way to send usable information faster than light. You can't use entanglement to send a warning or a bit or a picture ahead of a light beam. Every scheme that tries to exploit the instant-looking link gets crushed by the same fact. Local results are random, and the no-signaling rules of quantum mechanics keep causality intact. That leaves you in a very narrow corridor. The universe clearly allows non-local correlations that behave as if something outruns light by an absurd factor, but at the same time, it blocks every attempt to turn those correlations into a supraluminal message. The next natural question is, if you can't send information this way, can you at least stretch these entangled states across bigger and bigger distances, maybe across continents, maybe across the whole planet, and see whether this strange behavior still holds when the scale goes from miles to thousands of miles? How far can you push entanglement before the real world tears it apart? Does it die a few feet from the lab? Or does it keep working when you throw it straight into dirty, moving air over real terrain? This is where free space experiments come in. Teams set up telescopes on mountaintops, tens of miles apart, and blast entangled photons through open sky. The beams spread as they go. They get shaken by turbulence, they clip dust and water vapor, and most photons never make it. But the setup runs long enough that out of millions or billions of tries, a tiny fraction of photons do land in both detectors. Each observatory logs the arrivals, the measurement settings, and the outcomes. Afterward, the teams bring the data together and match coincident events, the ones that look like they came from the same entangled pair. When they crunch those numbers, they still see the same quantum correlation pattern that violates Bell's limits. That means the entanglement survived the whole brutal ride through the atmosphere, at least for the pairs that made it to both sides. So now, you're not just in a quiet optics bench world anymore. You're watching quantum non-locality show up across tens of miles of real sky. So if it survives tens of miles in air, what happens when you scale that up to hundreds or thousands of miles and you start bouncing these photons off satellites instead of just mountain peaks? Put a satellite a few hundred miles above Earth and you can set up a source on board that creates entangled pairs. One photon gets steered down to ground station A, the other goes to ground station B, maybe hundreds or even over 1,000 miles away. The trip from satellite to ground takes milliseconds at light speed, and in that time, the satellite is moving, the atmosphere is shifting, and the pointing has to stay precise enough that a tiny beam still hits a receiver dish. On the ground, each station runs its own detectors, its own random choice of measurement settings, and its own clocks. Over a run, they rack up hundreds of thousands of detection events. Later, they align to timestamps and filter out noise, including stray background photons. What's left are coincident detections that can be attributed to entangled pairs. The statistics from those coincidences show clear Bell inequality violations, just like in the lab. But now the separation isn't 40 feet, it's hundreds or thousands of miles, crossing weather systems. The same non-local pattern is now spanning entire regions of the planet. If that works through air and space, you might ask, can you also send entanglement through the stuff that already carries our internet? Or does all that glass, splicing, and city noise destroy it immediately? That's where fiber networks come in. In city experiments, physicists tap into standard telecom fiber, the same kind that runs under sidewalks and streets. They hook an entangled photon source into that network and send each photon of a pair to different buildings or labs, sometimes tens of miles apart, using existing underground routes. Along the way, those photons deal with absorption in the glass, scattering, bends, splices, and all the imperfections of real infrastructure. Most of them are lost before they reach the detectors, but again, you don't need most of them. You only need enough surviving pairs to build solid statistics. The detectors in each building log their events, and when the two ends share their data, the result is the same story. The entanglement is still there. Those successful runs are the backbone of early quantum internet links, real cables carrying real entangled states alongside ordinary data traffic. That sounds almost too good. So where is the difficulty? What's fighting you the whole way? Free space links deal with atmosphere and noise constantly. Photons can scatter off dust, air molecules, and turbulent cells, or just miss the receiver entirely as the beam spreads. Sometimes you only get one useful coincidence in thousands or millions of attempts. Fiber links have their own problems. Glass absorbs and scatters light. Connectors add loss, and thermal noise and detector dart counts pollute the signal. The trick is that you don't need a high survival rate to prove entanglement. You need a clear pattern in the data you do get. Single photon detectors are ridiculously sensitive, able to register individual photons that make it through all that abuse. The timing electronics can narrow down which clicks could have come from the same pair to billionths of a second or better. Even when the raw loss is brutal, the coincidences that survive can still show clean quantum correlations that stand far above the background noise. So the message from these experiments is harsh but clear. The world is hostile, but entanglement is tougher than your intuition says, as long as you play the statistics game right. Once you know you can hold entanglement over tens of miles in air, tens of miles in fiber, and hundreds or thousands of miles using satellites, the next question almost asks itself, how big can this get? Is there a practical upper limit, or is the only barrier engineering? Researchers are already talking seriously about global-scale quantum networks, with constellations of satellites acting as relay nodes and long-distance fiber links connecting major cities. You could, in principle, create entangled pairs where one photon ends up in North America and the other in Europe or Asia, then verify the same Bell-violating patterns across oceans. Push that further and you hit proposals that sound like science fiction, but are technically straightforward on paper. Test entanglement between Earth and the Moon. That's about 240,000 miles of separation, almost a light second. One photon to a lunar base, one photon to a ground station on Earth. The loss, pointing, and timing challenges are huge, but the physics says the pattern should still hold. The same non-local correlation stretched over almost a light second of distance. If that works, then every classical local influence explanation is under even more pressure, because now you'd be looking at a single quantum state spanning scales that our normal sense of cause and effect can't handle. So you end up with a picture where entanglement is not a tiny lab curiosity. It's a resource you can move through air, glass, and vacuum, across cities, countries, and potentially Earth-Moon distances, without the quantum pattern caring about the miles in between. But if the universe lets you stretch this weird connection across such huge scales, why does it still refuse to let you use it as a faster-than-light messaging system? What exactly stops you from turning these planet-spanning links into a superluminal communication network? If entanglement really stretches across cities, countries, maybe even Earth and the Moon, why can't you just flip that into an instant communication line and beat light at its own game? This is where the universe slams down a hard rule, and it's not optional. Quantum mechanics has a built-in constraint called a no-signaling theorem, and in simple terms it says this: you do not get to use entanglement to send information faster than light, no matter how clever you think you are. You can change how you measure your particle, you can switch settings on the fly, you can flip between different bases and try to encode bits into those choices. But on the other side, the local statistics do not budge. Every detector, looking only at its own stream of results, just sees randomness. You can't imprint a readable 1 or 0 into that randomness without also sending a normal light-speed message. Walk through a concrete setup. You and a friend share a huge pile of entangled photon pairs, distributed over a 1,000-mile distance. You decide you're going to be clever and send a bit. You say, if I want to send a 0, I'll measure my photons in the horizontal and vertical basis. If I want to send a 1, I'll measure in a diagonal basis, tilted at 45 degrees. On your side, you flip a coin in your head, pick a basis, and start measuring. Your detector clicks, and for each photon, you record horizontal or vertical in one case, diagonal up or diagonal down in the other. What does your friend see, sitting 1,000 miles away with her own detector wired up to their half of the entangled pairs? They do not see a clean 0 pattern versus a clean 1 pattern. They do not see the results suddenly shift when you change your mind about which basis to use. They see a stream of random outcomes, about 50% one result, 50% the other, with small fluctuations from noise and finite sample size. Nothing in that local stream of clicks tells them what you chose to do on your end. They can guess, but they cannot know. You might think, okay, but maybe the trick is not in single results. Maybe it's in subtle patterns. So your friend runs statistics on their own data, averages, correlations between neighboring times, whatever they can dream up. It does not matter. If they only use information from their end, the probabilities stay fixed by the entangled state in a way that is independent of your choices. That is what the no-signaling theorem is really saying. The math guarantees that when you sum over everything happening on your side, the other side's statistics are locked down, and your last-minute decisions do not leak through as a usable signal. Where then does the magic live, if not in any one detector's output? It lives in the joint data, in the comparison. After you both finish your runs, you take your timestamp logs and bring them together using some ordinary channel. Maybe that's an optical fiber link. Maybe that's a radio connection. Maybe you literally ship hard drives with gigabytes of time-tagged detection events. Only when you line up your entries with theirs, pair by pair, do the correlations pop out. You see, for this setting combination, you agreed this often, disagreed that often, and those rates violate Bell's inequality exactly the way quantum theory predicts. Look at what that means. The non-local structure is real, but it is only visible when you combine information from both wings of the experiment, after the fact, using signals that themselves cannot move faster than light. Before that comparison, each wing sees noise. After the comparison, you see a pattern that no local hidden variable model can match. The universe is basically saying, I'll give you non-local correlations, but I'm only going to let you see them once you respect the ordinary causal structure. Of course, people have tried to game this. Physicists have spent decades poking the boundaries, asking, is there some loophole that lets you squeeze a real faster-than-light message out of entanglement if you just design the protocol cleverly enough? You can delay measurements on one side. You can decide your basis after detecting whether a photon arrived or not. You can try to post-select only certain subsets of events that look promising. Every one of those schemes gets run through the actual quantum rules, not wishful thinking, and the outcome is always the same. If you respect the standard framework of quantum mechanics and relativity, you do not beat the no-signaling theorem. Whenever a proposal seems to break it, there is either a hidden classical channel buried in the setup, or a mistake in how the probabilities are being counted, or a misuse of post-selection that smuggles in extra information. The moment you clean up the reasoning, the apparent superluminal signal vanishes. The math is unforgiving here. The same theory that predicts these wild, Bell-violating correlations also strictly enforces that no observer can use them to send a message outside the light cone. So, where does that leave causality, the basic demand that causes come before effects in every frame that matters? Surprisingly, it leaves it intact. Entanglement behaves as if something faster than light connects measurement outcomes, because the correlations do not decay with distance and do not respect any normal delay you would expect from a signal. But when you zoom in on what is actually controllable, on what you can choose and what you can read out locally, every possible observable effect at one lab depends only on things inside its past light cone. You never get a setup where someone can send a warning into their own past and rewrite history. That's the brutal but reassuring headline. The universe lets reality look weird with non-local quantum states and space-like correlations, and at the same time, it keeps the causal order safe. You can stretch entanglement across miles, countries, maybe to the moon, but you do not get a time machine, and you do not get a faster-than-light modem. Which raises the next question that really tightens the tension. How does this sit next to relativity itself, a theory built entirely around light cones and local signals? And why don't these space-like quantum correlations rip a hole in that structure? Here's the really uncomfortable part. In a lot of these entanglement experiments, there isn't a single, universal answer to the question, which measurement happened first? The two detection events are set up to be space-like separated, which means that if you draw their positions and times on a space-time diagram, neither one sits inside the other's light cone. No light speed signal or anything slower can get from A to B in time to influence what happens there within that same run, and the same is true in reverse. In that situation, relativity says different observers, moving at different velocities, will disagree on the order. In some frames, A clicks first and B clicks second. In other frames, B clicks first and A clicks second. Both descriptions are valid. The equations do not pick a winner, and the quantum correlations show up the same way no matter which event you feel like calling the cause. So if even the basic before and after can flip depending on who's watching, what do different observers actually say about the same entanglement experiment? And how do they all still agree on the outcomes that matter? Take one observer sitting in the lab with the source and the two detectors fixed to Earth. In that lab, frame U might calculate that detector A's measurement happens a tiny fraction of a microsecond before detector B's. Now, add a second observer moving past in a fast spaceship, cruising at a significant fraction of light speed along the line between the detectors. When that observer does the same timing calculation using their own coordinates and their own synchronized clocks, the order can flip. Detector B may come out as earlier than detector A. The key is that neither observer gets to rewrite the raw joint probabilities. Each one assigns times and positions differently, but when they later sit down and compare data, the patterns of correlations are identical. They agree on how often the outcomes match or differ for each pair of measurement settings. Relativity doesn't give a special badge to any one frame that says this is the true story of who influenced whom. It only insists that the speed of light limit on signals hold in all frames, and quantum mechanics slots into that by making sure that nothing in the entanglement setup lets any observer see a faster-than-light message in their own local data. If that's how things work, you might be tempted to say, fine, maybe there really is a hidden true frame where some super fast influence runs from one detector to the other, in a definite order. We just happen to be in moving frames that scramble the story. But if that were the case, if there was a secret preferred reference frame built into nature, you'd expect it to leak into the experiments. You'd see tiny directional effects, small changes in the observed correlations depending on how the whole apparatus is oriented relative to that hidden frame, or depending on the time of day and the season as Earth rotates and orbits the sun and changes its velocity through space. So people went looking. They ran Bell tests with detectors separated east-west, then north-south. They repeated experiments at different times with Earth facing different directions in its orbit. They checked whether the strength of the Bell violation or the inferred minimum influence speed changed in a way that pointed to a special rest frame. Within experimental precision, nothing like that has shown up. The non-local correlations don't seem to care where Earth is in its orbit, how it's spinning, or which way the baseline between detectors points in space. As far as current data shows, there is no detectable preferred frame for these entanglement effects, no hidden cosmic ether that the experiments can read out. That raises a sharp question. If the ordering of events can flip from frame to frame and there's no detectable special frame to anchor some hidden influence, why doesn't relativity just collapse under this non-local behavior? What exactly is it protecting that entanglement never manages to break? The answer is that relativity's main concern is not with correlations, it's with signals, with anything that can change what is possible in another region of spacetime. Light cones define which events can be linked by cause and effect chains that respect the speed of light limit. As long as no one can use entanglement to alter the probabilities of outcomes outside those cones, the causal structure of spacetime stays intact. And that's exactly what the no-signaling theorem guarantees. In every entanglement experiment, the local statistics at each detector, the probabilities for up or down, horizontal or vertical, depend only on the local setup and the shared quantum state, not on which setting was chosen at the distant detector, or what outcome was seen there. You can tilt your polarizer, flip your basis, switch your settings at the last possible microsecond, and the other side's local probability distribution does not know or care. The correlations in the joint data can be non-local, but the knobs you can actually control do not let you reach outside your light cone and tweak someone else's odds. From relativity's perspective, that is what matters. So you end up with two theories making statements that sound, at first pass, like they should clash. Quantum mechanics, especially in its field theory form, tells you that quantum states are spread out, non-local objects, and that entangled states can link distant regions of space in one unified description. Relativity tells you that physical influences and information-carrying signals are confined to move inside light cones, and that there is no preferred global notion of now that applies to the whole universe. On paper, that sounds like a fight waiting to happen. In practice, when you write both theories carefully in a relativistic quantum field framework, they sit together without contradiction. In that framework, what you call a particle is an excitation of an underlying field that lives across spacetime, and entangled states are just particular ways those fields are correlated. The math is built so that operations associated with space-like separated regions cannot be used to change each other's local outcome probabilities, even though the joint state is non-local. That is the technical way of saying states can ignore distance, but signals cannot. The tension you feel is mostly in your intuition, which wants every correlation to come from a story about stuff moving around and talking to itself in ordinary space. If you want to really see how this hangs together under the hood, you have to look at that deeper picture where fields fill all of space, particles are ripples, and conservation laws and global constraints tie distant events together without sending messages between them. That is where the non-local state and the local signal limit meet in a single description, and where the idea of speed for these correlations starts to look like the wrong question. What does all of this look like when you stop talking about little particles at all and look at what the deeper theory actually says is there? In modern physics, the basic ingredients aren't tiny marbles flying around. They're quantum fields that fill all of space. There's an electromagnetic field, an electron field, a quark field. They're everywhere, all the time. When you say a photon is created, what you really mean is the electromagnetic field gets kicked in a very specific way so that a little ripple appears in it, a packet of energy that behaves like a particle. Now take that crystal in the lab that spits out entangled photon pairs. The process that happens in that tiny region, maybe a few micrometers across, doesn't just make two separate dots and fling them outward. It prepares a joint excitation of the field, a combined pattern in the electromagnetic field that stretches out along both directions at once. When the ripples travel outward and hit your detectors, you call them photon 1 and photon 2. But under the hood, they came from one unified disturbance in a field that already extended across the space between them. So when you later measure polarization at two distant points, you're not sending a signal from one photon to another after the fact. You're probing different parts of one non-local field state that was set up at the source. The weirdness isn't happening when the detectors click. It's already baked into how the state was prepared and how the field that underlies everything stores information about that process. How do those distant parts stay coordinated so tightly without anyone sending a faster-than-light memo across the gap? A big part of the answer is conservation laws. When the source process has to conserve total spin, total momentum, or total angular momentum, those rules apply to the joint state as a whole. If the total spin of the pair must be zero, then the field state is a superposition of up here, down there, and down here, up there, in just the right mix to satisfy that constraint. When you finally read out up at one detector, you're not forcing the other side to change on the fly. You're just narrowing down which branch of the already existing joint state you're in. Given that the total spin has to add to zero, once your measurement has locked in up on your side, down on the other side is already guaranteed. No message had to cross space to enforce that, because the state that connected both regions already respected the global rule from the moment it was created. Your measurement just exposes one slice of a structure that was non-local from the start. If that sounds abstract, think about how the theory actually calculates probabilities. In the path integral picture, a particle doesn't commit to one sharp path from point A to point B. The math tells you to consider every possible route through spacetime, even wildly zigzagging, looping, back and forth routes, and add up contributions from all of them with specific weightings. The final probability for a given outcome comes from that gigantic sum. Now apply that to two entangled photons. The calculation doesn't follow one definite path for photon 1 and one definite path for photon 2. It sums over all joint possibilities, where both photons explore all compatible routes and all compatible spin or polarization configurations at once. The non-local correlations you see in the data aren't something you bolt on later. They're embedded directly into how you compute the probabilities. You never had a story where each photon carried its own tidy script along a clean trajectory. You had a big, holistic object in the math that covers the whole experiment. This one big state idea isn't limited to pairs either, and this is where things get even serious. In many body systems, like solids, you can have enormous numbers of electrons sharing quantum correlations over macroscopic distances. In a crystal, electrons don't just sit on individual atoms, they form bands, and their states can spread out over millimeters or centimeters of material. In some phases of matter, the system can act like a single coherent quantum object. Superconductors are a classic example. Below a critical temperature, electrons pair up into what are called Cooper pairs, and those pairs condense into a collective state. Electric current in a superconductor flows with effectively zero resistance because the electrons aren't behaving as independent particles bouncing off impurities. They're locked into a coherent wave-like state that extends through the material. That coherence is a form of large-scale entanglement built into a many-body system, and you can see its effects in current that flows indefinitely in a loop without decaying. So the natural question is, how far can you actually stretch a quantum state in practice? How big can this get before the world shreds it? Experiments with Bose-Einstein condensates give a pretty dramatic answer. You take a gas of atoms, trap them, and cool them down to billions of a degree above absolute zero. At those temperatures, their individual wave packets spread out, overlap, and the whole cloud can drop into one quantum state. When that happens, the atoms don't behave like a loose pile of separate points. They act like one giant matter wave, with phase relationships and correlations that cover the whole trap. Distances of millimeters or centimeters might sound tiny in everyday units, but at atomic scales, that is enormous, millions of atomic spacings across. Interference experiments and correlation measurements show that these condensates can maintain entangled or highly coherent states over that whole region, at least for limited times before interactions with the environment break them down. All of this points in the same direction. The basic objects of the theory are fields and global quantum states, not little billiard balls pinging messages around. Entanglement is what it looks like when those global states have strong correlations between distant regions. The speed of that connection isn't a meaningful number inside the math, because nothing actually races from one side to the other when you measure. You're just reading out different parts of a pre-existing non-local structure. But if the universe is built out of these big, fragile quantum states, and if they can, in principle, stretch over centimeters, meters, miles, or more, why don't you see this kind of entanglement in the everyday objects around you? Why doesn't your coffee mug act like a giant Bose-Einstein condensate, or your car or your own body show obvious quantum weirdness at human scales? That's where the next piece of the story hits, the process that constantly fights against coherence and entanglement, and silently drives most big systems back into the classical world you're used to. How hard is it to keep quantum weirdness alive when you move from single particles to anything even slightly bigger? The answer is brutally hard. Try to entangle a grain of dust or a tiny mechanical mirror you can just barely see under a microscope, and the entire environment turns against you. Every stray photon of light, every air molecule that bumps into it, every tiny thermal vibration is an interaction that leaks information about the system into the surroundings. That leakage destroys the clean quantum correlations you work to create. This process has a name, decoherence, and it is the main reason the everyday world looks classical instead of obviously quantum. You can think of decoherence like this. Your system starts in a delicate superposition or entangled state, with different possibilities still on the table in the quantum description. The moment it interacts strongly with the environment, those possibilities become tied to different environmental states, and the overall pattern of interference that gave you quantum behavior gets washed out. You do not need a conscious observer. You do not need a measurement device. You just need the system to bump into the world in the wrong way. For small particles in a well-controlled vacuum, you can avoid that for a while. For bigger objects, the number of ways that can couple to the environment explodes, and decoherence hits almost instantly. How fast does this happen in real systems? The numbers are all over the place, and they depend heavily on temperature, shielding, and size. For electrons moving around in a warm solid, constantly colliding with other electrons, vibrating atoms, and impurities, coherence times can be insanely short, down at the level of femtoseconds, trillionths of a second. Any coherent quantum phase relationship you try to maintain between different possible states gets scrambled before you can do much with it. In carefully engineered systems, you can stretch those times a lot. Superconducting qubits, the building blocks of some quantum computers, are physical circuits maybe a fraction of an inch across, cooled below a tenth of a degree above absolute zero. In that regime, electrical resistance essentially vanishes, thermal noise drops, and you can get coherence times of microseconds to milliseconds. That still sounds tiny, but it's enough to perform dozens or hundreds of quantum logic operations if you move fast and correct errors. Other platforms push even further. In trapped ion systems, where you hold single ions or small ion chains in electromagnetic traps in ultra-high vacuum and cool them down with lasers, individual qubits can maintain coherence for seconds, sometimes more. That means the state of the ion really does retain a stable quantum phase relationship over macroscopic timescales, as long as you keep the outside world under tight control. So you have a huge spread from trillions of a second in noisy solids up to seconds in ultra-clean, ultra-cold systems. But is it only tiny particles and microscopic circuits that can show this behavior, or can you actually put bigger, more complex objects into clear quantum superpositions, things you would normally think of as classical chunks of matter? The answer is you can, but it takes serious work. One famous line of experiments sends large molecules with thousands of atoms and sizes of tens of nanometers through double-slit or grating interferometers. You prepare a beam of these molecules, get them cold and slow enough, and send them through. On the far side, you see an interference pattern build up, just like with electrons or photons. That interference pattern is direct evidence that each molecule behaved like a wave that went through multiple paths at once and then recombined. You do not get that pattern if each molecule was always on one definite path with no coherent phase relationship. So even fairly complicated, heavy molecules can be put into spatial superposition states. The catch is you only see this when you isolate them extremely well. Vacuum chambers, cooling, shielding from vibrations and stray radiation. Take away that protection, the interference vanishes fast. Decoherence wins. So why doesn't this sort of thing show up in the stuff sitting on your desk? Why doesn't your coffee mug act like a giant Bose-Einstein condensate? Or your car or your own body show obvious quantum weirdness at human scales? That's where the next piece of the story hits. The process that constantly fights against coherence and entanglement, and silently drives most big systems back into the classical world you're used to. In practice, once a macroscopic object like your mug is constantly slammed by trillions of air molecules, thermal photons from the room, and interactions with the table, any delicate pattern of phase relationships between well-defined alternatives gets spread out into an enormously complicated mess. The quantum description is still there, buried in an enormous entangled state of mug plus air plus photons plus everything else. But for all practical purposes, any interference between the different branches of that state is gone. You cannot recombine them. You cannot access the coherences. What you see is a mug with a definite shape and position, obeying classical-looking rules, because every attempt to treat it as a clean quantum object gets erased by raw environmental coupling faster than you could ever control. That is the core reason everyday objects don't display obvious quantum behavior. It is not that they have stopped being quantum in some deep sense, it is that their quantum properties have been scrambled and dispersed into so many degrees of freedom that the interference effects are, practically speaking, unrecoverable. Decoherence has turned clean superpositions into classical-looking mixtures, long before your eyes or instruments get involved. When you try to scale up devices that actually use entanglement, all of this turns into an engineering nightmare. If you want entangled states to survive over inches or feet and last longer than microseconds or milliseconds, you have to wage a constant war against decoherence. That means vacuum chambers to remove air molecules, cryogenic refrigerators to kill thermal noise, electromagnetic shielding to block stray fields, vibration isolation to keep mechanical motion under control, and error correction codes to repair the damage you cannot avoid. Quantum computers are the clearest example. Every qubit you add to your system multiplies the number of ways it can couple to noise. As you try to entangle more qubits over larger distances on a chip or between chips, you have to manage crosstalk, material defects, background radiation, and more. The performance data you see in research papers, coherence times, gate error rates, photon loss statistics, readout fidelity, all tell the same story. Progress is real, but the environment is relentless. So you end up with this contrast. On one side, the theory says you can, in principle, entangle huge systems and stretch quantum states over large distances. On the other side, decoherence tells you that nature will try to kill those states as fast as it can once you move beyond carefully protected setups. And yet, even with those constraints, we already have technologies that use entanglement in the real world, over real distances, in actual networks. So the next question is, what can you actually do with this stuff today? And how does a universe that forbids faster than light signals still let you use these non-local links for secure communication and new kinds of networks? So what does a universe full of non-local quantum states give you in practice if it still refuses to let you send a single bit faster than light? One answer is it gives you a new kind of security, not based on human promises or mathematical guesses, but on the way nature itself handles information. Quantum key distribution is the clearest example. In a typical setup, you and a partner share entangled photons sent over tens of miles of fiber. Each of you measures your photons in randomly chosen bases, logs the results, and later uses a normal light speed channel to compare which measurement settings matched. From the runs where your settings line up, you both see strongly correlated outcomes. You can turn that shared randomness into a secret key, a long string of bits only you two should know. Now add an eavesdropper in the middle. If they tap the line and start measuring photons, they inevitably disturb the entanglement. Their measurements break the quantum correlations and inject errors into the statistics. When you and your partner compare a subset of your data, the error rate spikes above a known threshold. That spike is physics shouting, "Someone touched the channel." You throw away that key and try again. No faster than light messages, but a kind of security guarantee that classical systems can't match. Scale that idea up and you get city-scale quantum links. There are test beds where banks and research labs share fiber running under streets and across bridges, with distances of tens of miles between nodes. The quantum systems sit alongside normal telecom gear, sending faint single-photon signals on dedicated wavelengths. They constantly log how many secure qubits per second they're generating, often in the kilobit per second range, track the error rates in real time, and automatically decide whether the link is quantum good or not. If the noise rises or the key rate drops below a set threshold, the system does not blindly trust the quantum channel. It falls back to classical methods, flags the link for inspection, or reroutes traffic if possible. You end up with a hybrid network, where the quantum layer provides fresh shared keys when conditions are good, and conventional cryptography carries the load when conditions are bad. The key point is the hardware isn't living in a whiteboard diagram. It's hanging in racks, plugged into fibers buried under actual city blocks. Now push the scale out to satellites again, but this time with a direct goal. Distribute encryption keys between ground stations thousands of miles apart. A satellite a few hundred miles up generates entangled photon pairs and sends one photon down to city A, another photon to city B, maybe on different continents. Most photons never arrive. They get absorbed in the atmosphere, miss the receiver, or die in the optics. But over minutes of operation, enough pairs get through that the two ground stations can harvest a shared random key. Once again, if someone tries to intercept those photons, the error pattern in the correlations betrays the intrusion. The link is weak, fragile, and slow compared to classical broadband, but the keys that survive can be proven secure under clear assumptions. This is a direct use of non-local correlations across thousands of miles, and still, nothing in the protocol violates the light speed limit. The key agreement, the reconciliation, and the final security checks all run over normal classical channels. Underneath all of this sits something even more basic: the need for high-quality randomness. Classical computers are terrible at that on their own. They run deterministic algorithms and only fake randomness through complicated math. Quantum devices can do better. Some commercial hardware already uses quantum processes to generate random numbers. For example, shining very weak light on a detector and counting individual photons, or measuring vacuum fluctuations in an optical or electronic mode. Each detection event is fundamentally unpredictable, and over billions of bits, the output streams pass extremely tough statistical tests. You don't see patterns, biases, or repeats that classical pseudo-random generators can accidentally introduce. That randomness feeds into encryption keys, simulations, and protocols where you really do not want hidden structure that an attacker can exploit. Again, no faster than light anything, but a direct benefit from quantum behavior that you can buy in a box and plug into a network. All of this points towards something bigger that is still very much under construction, a quantum internet. Researchers are already linking labs across campuses or cities using entangled photons and quantum memories. They use a trick called entanglement swapping, where you entangle A with B and B with C, then perform a joint measurement at B that effectively leaves A and C entangled, even though they never interacted directly. Do this repeatedly through a chain of nodes, and you can, in principle, create entanglement between distant endpoints without needing a single perfect loss-free link. These prototype networks are full of numbers that sound very dry, but mean everything if you care about scaling, fidelities that tell you how close your real states are to ideal ones, loss budgets that track how much signal you can afford to lose before the protocol collapses, error rates that decide how much correction or redundancy you need. Every experiment that pushes entanglement across another campus or through another set of intermediate nodes feeds directly into design plans for continent-scale networks, and eventually maybe global ones. So you end up in a strange position. The same theory that says you cannot send a text faster than light, that slams the door on superluminal signals and time travel hacks, is quietly giving you new ways to secure communication, new tools for networking, and new resources like certified randomness, all built on top of non-local correlations that act as if distance barely exists. Entanglement never lets you break the speed limit, but it absolutely lets you use the structure of quantum reality in ways no classical system can copy. And that brings you back to the original question you started with. Is there something faster than light? For signals, for anything that can push on cause and effect, the answer stays no. The speed of light is still the limit. But for correlations, for the way information is stored in quantum states that stretch across space, you are dealing with something that does not fit into the usual idea of speed at all. It looks superluminal, it behaves as if it ignores distance, and it powers technologies that are only just starting to appear. The universe didn't give you a faster-than-light courier. It gave you a non-local structure under the surface, and right now you're only beginning to learn how to use it. When physicists talk about quantum teleportation, what is actually moving if you're not allowed to send anything faster than light? The key point is this: teleportation does not move matter, it moves a quantum state. You start with some system in an unknown state on your side, and you end with a different system, far away, in that same state, while the original is gone. There is no copy left behind. The state isn't duplicated, it's transferred. The protocol uses two ingredients: shared entanglement between you and the receiver, plus a normal classical message. You do a special joint measurement on your side that both destroys the original, you never see it again, but also projects the receiver state into a state that's closely related to what you started with. To finish the job, you send two classical bits that say, in effect, my result was type 0, 1, 2, or 3. Based on those two bits, the receiver applies one of four possible local operations to their photon. After that, their photon carries the original polarization, and there is no copy on your side. How far did people manage to push this idea before it broke under loss and noise? Did it stay a tabletop trick, or did it scale? Over time, teleportation was demonstrated over longer and longer channels. Teams sent states through kilometers of optical fiber in the lab, then through free space links between buildings separated by several miles. Later, space-based experiments teleported quantum states between ground stations and satellites hundreds of miles up, using entangled photons and very careful timing and pointing. In all of these cases, the big questions are, how often does the protocol actually succeed, and how close is the final state to the original one? That closeness is measured by fidelity, a number between 0 and 1. In good experiments, even with real-world losses and noise, fidelities above 80 or 90% are common, which is far beyond what you'd get by doing a simple measure and guess strategy with classical information. As the distances get longer, losses go up, and success rates drop, but the runs that do succeed still show that the state really was transferred using entanglement plus classical bits. So if the state appears at the other side right after you do your measurement, why doesn't this count as faster than light teleportation? The answer is buried right in the protocol. Before the receiver gets your two classical bits, their photon is in a kind of scrambled state, a mixture of possibilities that by itself does not encode any useful information about your input. They can measure that photon all they want before the classical message arrives. They will only see random outcomes consistent with the overall statistics of the protocol. They cannot tell which input state you had, and they cannot tell which result you got in your Bell measurement. The entanglement gives you a channel that is ready to carry the state, but the classical bits are the key that unlocks it. Until those bits arrive at light speed or slower, the receiver cannot know which correction to apply, and their system does not carry a readable copy of your input. Once the bits arrive, they do a simple local operation, and only then does the teleported state become fully available. That timing is exactly what keeps teleportation from being a faster-than-light communication method. If you tried to use it to send a message into someone's past, you'd run straight into the same no-signaling wall as before. How do you even know in practice that you really teleported a quantum state and didn't just cheat with a classical approximation, like measuring, writing down the results, and rebuilding something similar on the other side? Teleportation experiments answer that with numbers. They report success probabilities, which say how often the protocol actually yields a valid outcome given the lossy channels and imperfect detectors, and fidelities, which say how close the output states are to the targets you were trying to send. There's a benchmark here. If you take an unknown quantum state, measure it as best you can with classical tools, and then prepare a new state based on that measurement, there's a maximum average fidelity you can reach. For simple two-level systems, that best classical measure and guess strategy tops out at a specific value below 1. When experiments show average fidelity significantly above that classical ceiling over many different input states, that's your proof that something genuinely quantum is happening. The data is telling you, no classical copying strategy could have produced this level of agreements between input and output. So quantum teleportation ends up as one more example where entanglement looks like it's doing something that should not be possible, states jumping from place to place, while the details keep you safely inside the light speed limit. The state transfer is real, the original is destroyed, the copy appears far away, and yet the classical bits that finish the protocol never outrun light. It's another reminder of the same theme you've seen all the way through. The universe lets you use non-local quantum structure in powerful ways, but every time you try to turn that into faster-than-light control, the rules close in and force you back into line. So far, you've seen entanglement as something that links particles across space. But it's also the thing that makes quantum computers more than just weird, expensive calculators. At the basic level, the difference starts right at the smallest unit of information. A classical bit is simple. It's either 0 or 1 at any moment, one definite state. A qubit is not locked like that. It can be in 0, in 1, or in a superposition that's some 0 and some 1 at the same time, with specific weights and a relative phase. On its own, that's just a fancy way of saying you get different probabilities when you measure it. The real jump comes when you have many qubits together and you entangle them. Then the whole state of the system can't be written as this qubit is like this, that qubit is like that anymore. You get a joint state where the whole pattern matters, and that pattern can encode relationships that no simple collection of separate bits can mimic. That entanglement is not just a side effect, it's a resource, almost like fuel for certain algorithms. You can ask, is this just theory, or are there actual machines pushing large entangled states around right now? And the answer is yes, with all the usual caveats. Superconducting quantum processors put qubits in tiny loops of metal on a chip cooled down near absolute zero. Trapped ion devices line up charged atoms in vacuum chambers a few inches across and manipulate them with lasers. Photonic platforms use single photons moving through waveguides on silicon. Depending on the platform, you're talking tens to thousands of physical qubits today. Coherence times in these devices range from microseconds to milliseconds, not long by human standards, but long enough to run quite a few gate operations if you move quickly and correct errors. Gate error rates might be around 1 in 1,000, or in better setups, down around 1 in a million, depending on the specific technology and how hard you push it. The core trick these machines have to pull off is creating and controlling entanglement on demand. That's what 2-qubit entangling gates are for. A single qubit gate just rotates the state of 1 qubit, like turning a knob on a point on the Bloch sphere. A 2-qubit gate, like a controlled knot or a controlled phase, actually ties the states of 2 qubits together, building correlations that weren't there before. String a lot of those gates across a register, and you can build wildly complex entangled states spread over many qubits. In the lab, these gates get tested and calibrated using tomography. You prepare a set of known inputs, run the gates, and then measure the outputs in different bases. From all those results, you reconstruct what the operation the gate actually performed and compare it to the ideal. That gives you a gate fidelity, a number that tells you how close you are to perfect control. Why does all this effort to keep entanglement alive matter for speed? What do you actually gain that a classical supercomputer can't fake? For some algorithms, the raw advantage is tied directly to the entangled structure of the intermediate states. Take Shor's factoring algorithm. It uses a register of qubits prepared in a big superposition of many values at once, and then applies a sequence of entangling operations that encode periodic structure into the global quantum state. At the end, a measurement pulls out information about that period, which lets you factor large integers much more efficiently than any known classical method. The intermediate state, before you measure, is highly entangled across many qubits. Trying to track that full state on a normal computer requires memory that grows exponentially with the number of qubits. The same story shows up in quantum simulation, where you model molecules, materials, or quantum field systems with qubits. The natural states of those systems are often deeply entangled, so a device that can natively host those states has a direct edge. That doesn't mean every task runs faster on a quantum machine, or that building one automatically breaks all encryption, but it does mean there are problems where entanglement gives you access to parts of the computation space that are effectively blocked off for classical hardware. If you can prepare and manipulate those structured, entangled states with low enough error, you can explore and exploit patterns that a bit-based system would need ridiculous resources to even represent. So when people talk about quantum advantage, what are they really claiming? And how do you know when entanglement is actually doing something you couldn't reproduce with clever classical tricks? Most current demonstrations focus on specific tasks that are believed to be hard for classical algorithms, like sampling from complicated probability distributions defined by random quantum circuits. The quantum device runs a given circuit many times, spits out bit strings according to some messy distribution, and the researchers compare how long that takes and how well the distribution matches the theoretical prediction to the best classical simulations they can manage. The important numbers are things like wall clock runtime, the number of samples produced, measures of how close the observed distribution is to the ideal one, and the error bars on all of that. Under the hood, these random circuits are generating large entangled states across dozens or hundreds of qubits before measurement. Simulating those states exactly on a classical supercomputer quickly hits memory limits because the number of amplitudes you'd have to track doubles with every added qubit. When a quantum device can generate and sample from these states in minutes or seconds, while classical codes struggle for days or need wild amounts of hardware to keep up, that's where people say advantage. To be clear, the details are messy, and classical methods keep improving too, sometimes closing claimed gaps. But the trend is clear. The more deeply and widely you can entangle your qubits while keeping errors under control, the more you can push into regions of computation space that classical machines find expensive to reach. Behind every serious quantum advantage claim, there's a device juggling massive entangled states that we simply cannot track amplitude by amplitude on ordinary hardware. And that loops you straight back to the core theme of everything you've seen. Entanglement is not just a spooky speed question, it's a structural feature of quantum states. It lets you tie distant particles together. It lets you teleport states. It lets you build networks and new cryptographic tools. And it lets you explore computations that blow past classical limits. But at every step, when you try to turn that structure into faster-than-light signaling, you hit the same wall. The non-local state is real, the correlations are real, the computational power is real, and the speed of light limit on actual information is still locked in. Why does the idea of faster-than-light messages keep coming back? Even though the theory and the experiments keep killing it, every few years there's a new proposal, a new claim that this time, finally, entanglement has been turned into a supraluminal phone line. The pattern is almost always the same. Someone says, let's encode information not in the outcomes, but in the choice of measurement basis. Or let's only keep certain runs of the experiment, post-select on the cases we like, and throw away the rest. Or let's use delayed choice tricks, where we decide how to measure after the photons are already on their way and hope that retroactive magic will appear. On a whiteboard with hand-waving, these schemes can look like they outsmart the no-signaling theorem. The problem is, when you stop hand-waving and actually run the numbers using the full rules of quantum mechanics, or when you implement a simplified version of the protocol in a real lab, the apparent faster-than-light advantage disappears. If you try to encode a bit in your choice of basis, the other side's local statistics still come out the same, no matter what you picked. If you try to keep only certain outcomes, post-selection quietly sneaks in a dependency on classical communication, because to decide which runs to keep and which to toss, both sides need to compare notes. Without that comparison, each lab just sees its own random stream. This is the core failure mode, again and again. Locally, you never see a change. The marginal probabilities for each outcome at each detector stay fixed by the shared quantum state and the local measurement setting, not by what the distant party is doing. Any attempt to filter or condition the data in a way that seems to reveal a pattern ends up relying on information that had to come in at or below light speed from the other side. Once you account for that, the superluminal part evaporates. You might think, fine, but what if all of our Bell tests and entanglement experiments so far have missed some hidden classical mechanism, maybe a subtle bias where only some events get detected, or the measurement choices aren't as free as they look? That's exactly why people spent so much effort on closing loopholes in Bell tests. Early experiments had detection loopholes. Their detectors missed a lot of entangled particles, so you could imagine that only a subset with special properties was actually being counted, and a clever local hidden variable theory could hide in that gap. They also had what's called the freedom of choice loophole. If the settings chosen at the detectors, the angles or bases, were somehow correlated with the hidden variables carried by the particles, then you could fake a Bell violation while staying fully classical and local underneath. Modern experiments attack these problems head-on. They use near-perfect detectors that catch almost every photon or particle that arrives, shrinking the room for undetected events. They use ultra-fast random number generators, often based on quantum processes themselves, to choose measurement settings on the fly, milliseconds or microseconds, before detection, so there's no time for any local coordination.
And researchers didn't stop there, because you can still ask, what if the hidden coordination was set up way in advance, long before the experiment started? What if the entire lab's randomness is secretly biased by some deep unknown mechanism? That's where cosmic Bell tests come in. In those experiments, the measurement settings are chosen based on light arriving from distant astrophysical sources, stars or quasars billions of light years away. The idea is brutal. If you use the color or arrival time of those photons to set your detector angles, any classical hidden variable story that tries to coordinate the particle properties with the settings would have had to arrange that correlation back when that starlight left its source, long before Earth even formed. Teams have run these cosmic Bell tests and still see violations of Bell inequalities in the data. Even when the choices are driven by distant starlight, the correlations between entangled particles refuse to fit any local hidden variable model. That doesn't prove literally every imaginable loophole is gone, but it pushes classical explanations into a corner so small that they start to look like conspiracy theories baked into the initial conditions of the universe. So why does the dream of faster-than-light messaging refuse to die? Why do headlines keep popping up claiming that someone has finally cracked it? It's because your intuition keeps misfiring on the same point. The data say instant correlation. Your brain hears instant signal. You see measurements match up over miles or hundreds of miles with no time for a light speed message in between, and it feels like there's a channel there just waiting to be used. The tight entanglement patterns, the big Bell violations, the teleportation demos, they all look like communication wanting to happen. The whole job of this part of the story is to burn in the difference so it sticks. Correlation is not communication. Entangled states can be non-local, but the probabilities you can actually control and read locally still respect the light cone. Every attempt to hide a signal in basis choices or in post-selected subsets or in delayed choice tricks slams into the same wall when you do the full calculation. The non-local part of quantum mechanics is real, and so is the speed limit for any usable signal. So the next time you see a claim that someone used entanglement to send a message faster than light, you'll know what question to ask first. Did they actually change the local statistics at the other end without any classical link, or did they only find a clever way to see correlations after comparing data at normal speeds? If it's the second, it's not faster than light. It's just the same strange universe doing what it's always done. If the data won't let you send faster-than-light messages, but it clearly won't fit into a simple local picture either, where do you put the weirdness? Do you shove it into multiple universes, hidden waves, backward-in-time effects, or a rigged cosmic script from the Big Bang? Different interpretations of quantum mechanics give you different answers, and they all agree on one thing. None of them actually hand you a faster-than-light channel. Take the many worlds view first. In that story, there is no collapse of the wave function at all. The global quantum state just evolves smoothly according to one clean rule, always, everywhere. When you measure an entangled particle, you don't force a single outcome and destroy the rest. Instead, you, your apparatus, and the particles all become entangled, and the universe branches into versions where each possible outcome happens. You experience one branch, someone else experiences another branch, but the math keeps all branches together in one global wave function. In that picture, the spooky action you thought you saw when you measured one particle and instantly knew about the other is just bookkeeping. You and the distant particle were already part of a combined state that linked all outcomes. Your measurement sticks you into one branch where your result and the distant result line up correctly. There is no signal shot across space, just a single big wave function updating in a way that was fully determined by its previous shape. Now look at a very different style, Bohmian mechanics, also called pilot wave theory. Here, particles always have exact positions and follow definite trajectories. The randomness comes from not knowing their initial conditions. On top of that, there is a guiding wave, mathematically the same wave function as in standard quantum mechanics, that tells particles how to move. But this wave does not live in ordinary three-dimensional space. It lives in a high-dimensional configuration space that encodes all particles at once. In that view, non-locality is not hidden, it is right in your face. The pilot wave that guides one particle also depends on where other particles are instantly, even if they are far away. The price of having particles with definite properties is a wave that connects distant parts of the universe with no respect for the light speed limit at the level of description. You get a clear ontology, but it is deeply non-local. Still, even there, when you calculate what observers can actually see and signal, you get the same no faster than light constraints as ordinary quantum mechanics.
Another group of ideas try something even more radical. They let some influences run backward in time at the microscopic level. These are retrocausal models. In that kind of story, what you choose to measure in the future can influence the state of the system in the past in a carefully constrained way. The correlations you see in Bell experiments do not require an influence that leaps across space in the present. They can be drawn as a zigzag in space-time, going backward along one leg and then forward along another. From the right viewpoint, everything stays inside light cones, just with cause and effect allowed to flip directions at the quantum level. But notice what hasn't changed: the actual probabilities for measurement outcomes, and the rule that you cannot use those influences to send a controllable message to your own past. So far, these models are mostly different stories wrapped around the same predictions, not new physics you can test separately. Then there's the most extreme move: superdeterminism. Here, you attack Bell's argument at a different point. Bell inequalities assume that experimenters can freely choose their measurement settings, independently of whatever hidden variables the particles are carrying. Superdeterministic theories say, no, that freedom is an illusion. The settings you pick, the random numbers your devices spit out, even your decision to run the experiment are all correlated with the hidden variables from the very beginning of the universe. In that case, you can keep locality and realism. Bell's freedom of choice assumption simply fails, and the observed correlations are explained by a giant, prearranged pattern baked into the initial conditions. Local realism survives, but at the cost of turning the universe into something that looks like a fine-tuned conspiracy, where every attempt to test a theory was already scripted to give the quantum-looking answer. Again, right now, you don't get different experimental predictions out of this, just a very heavy philosophical commitment. So across all of these views, what actually changes and what doesn't? The equations used to calculate outcomes in experiments stay the same. The probabilities for different measurement results stay the same. Bell violations still show up. The no signaling theorem still holds. In many worlds, no branch can talk to another faster than light. In Bohmian mechanics, the pilot wave is non-local, but the observable statistics don't let you exploit that for superluminal messages. Retrocausal models just reroute the explanation through time, but do not let you send a usable signal to yesterday. Superdeterminism throws away genuine randomness and free choice, but as long as it reproduces standard quantum predictions, it inherits the same operational speed limit. That's the key point you need to hold on to. These interpretations are different stories about what is really happening behind the scenes. They move the weirdness around into branching universes, hidden waves, backward in time influences, or a fixed cosmic script. But they don't, as currently formulated, give you a knob you can turn to send a bit faster than light. They're not new tools. They're different narratives sitting on top of the same set of experimental facts. And that brings you right back to the core tension that started this whole journey. At the level of raw data, quantum entanglement shouts non-local, while relativity keeps shouting no faster than light signals. Every attempt to resolve that tension, every interpretation, keeps the same pattern: strong correlations that ignore distance and the rock-solid speed limit for anything that can count as information. So the final question is, what does that tell you about how to read the phrase something faster than light? And how should you think about speed, causality, and reality after you've seen how far the universe is willing to bend without ever quite letting you break it? So after all of that, what's the blunt answer to the question in the title? Are these entanglement correlations actually faster than light? It depends what you mean by faster. If you mean, do the correlations show up across any distance with no time delay you can detect? Yes, they do. You can spread entangled particles over tens of miles, hundreds of miles, maybe one day hundreds of thousands of miles. And when you line up the data, the pattern is just there, as if the gap between them never mattered. In that very narrow sense, the speed of the correlation looks infinite. No lag, no fall off with distance. But if you mean, can you send a controllable message? Can you poke something here and force a readable change there, outside the light cone? The answer is still no. Every time you try to turn that instant-looking link into a signal, the statistics on each side stay stubbornly unchanged. The universe gives you non-local patterns and still refuses to let you push cause and effect faster than light.
So what is light speed really the limit of, if not every kind of connection? Light speed limit isn't about correlations in a state. It's about influence, about how fast you can push causes into effects that someone else can see without extra help. It's the cap on how fast energy, information, and controllable signals can move through spacetime. Entanglement gets around that because the thing you're looking at isn't a signal being sent later, it's structure baked into a joint quantum state from the moment those particles are created. When you finally measure, you're not transmitting anything across the gap. You're revealing one slice of that shared structure at your location. Someone else, far away, reveals another slice at theirs. The correlations were written into the global state from the start. They don't have to travel. That's why all the language about spooky influence is misleading if you take it literally. There isn't a little messenger that leaves one detector and races to the other faster than light. There's a single non-local quantum state spread over both regions. Measurement doesn't kick off a new process that crosses space, it just selects one outcome from the menu that the state already encoded, subject to global constraints like conservation of spin and energy. It feels like something jumped across the gap because your classical intuition keeps trying to redraw everything in terms of local objects with local properties. The actual description lives at the level of the combined system, not the parts. When you put the whole experimental story together, from crystals a few inches wide to satellites hundreds of miles up, you're forced to swallow a bigger conclusion. The universe is more connected than you were ever told in school. The data say you cannot, in general, break the world into isolated, independent chunks that only talk by sending particles back and forth. Objects can share a single quantum state that stretches across vast distances. What happens here and what happens there are not two separate stories glued together after the fact. They're different aspects of one global pattern. Space starts to look less like a bunch of separate boxes and more like a stage where the full arrangement, the full wave function, really matters. That doesn't mean everything is always maximally entangled with everything else in some usable way. Decoherence and noise shred most large-scale quantum links before you ever notice them. But the fact remains, when you take extreme care, you can maintain and test non-local states over distances that would have sounded absurd a few decades ago. And we're not done pushing. Future experiments are going to aim well beyond ground-to-satellite distances. As more infrastructure goes into space, you'll see proposals to entangle stations on Earth with stations on the Moon, about 240,000 miles away, close to a light second. Later, maybe Earth-Mars links with light travel times of minutes. Those tests won't just be because it's cool, they'll be aimed straight at the next obvious question. Does gravity or curved spacetime or being in different gravitational potentials change quantum correlations in any measurable way? You can imagine detectors on orbiting platforms, quantum repeaters sitting at Lagrange points, ultra-precise clocks comparing time dilation while entanglement is being swapped and stretched. If the same Bell-violating patterns hold across Earth-Moon or Earth-Mars scales, with different gravitational fields and curved paths in between, that will be an even louder statement that quantum non-locality doesn't care about the distances you throw at it, or about gentle space-time curvature either. And that sets up the final punchline you walk away with. You live in a universe where nothing can send a signal faster than light, where every usable influence, every bit of energy, every message you can actually control is trapped inside light cones and bound by Einstein's limit. At the same time, you live in a universe where the underlying quantum state of reality can be entangled across hundreds, thousands, maybe millions of miles in ways that act as if distance barely exists at all. The speed limit survived. Your old intuition, the one that said local pieces, local causes, local everything, did not. Once you see that, you can't unsee it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.